Beginning in October of 2024, Netflix began airing Orb on the Movements of the Earth, which has been receiving overwhelmingly positive reviews from critics and fans. This series is set in the early 15th century and depicts various characters working to develop the theory of heliocentrism, that the sun is the center of the cosmos as opposed to the Earth, all the while under threat from the Inquisition, which has deemed such propositions as heresy. But how much of the history did they get right? And how much is made up? In today's video, we'll take a look at Orb on the Movements of the Earth and compare it with the real history of astronomy before the telescope. Before we go any further, I'll issue a minor spoiler warning. While I'm going to avoid spoiling the plot as much as possible, I'm going to have to discuss some of the historic points that are referenced, and clever viewers may be able to infer the larger plot points surrounding them. Thus, if you haven't watched the series and you care about such things, consider saving this video to watch later. On the other hand, having watched this video first may help enhance your viewing experience, as the series is packed with subtle historical references. One of the central themes of this series is the pursuit of truth in the face of adversity, with the truth in question being the nature of the arrangement of the cosmos, as expressed by the competing models of geocentrism and heliocentrism, which place the Earth and Sun at the center of the cosmos respectively. So, let's begin by understanding where geocentrism came from. During the time in which this series takes place, astronomers hadn't been able to measure the distances to stars. At that time, all astronomers could tell about the stars was that they didn't seem to move relative to one another. Thus, astronomers assumed that the stars were all affixed to a giant sphere of stars which rotated around us. This left philosophers of the time to wrestle with how the sun, moon, Earth, and planets were all arranged within this sphere. But weighing on that discussion were philosophical assumptions that date back to the 4th century BCE with Aristotle. Specifically, Aristotle's model is discussed in episode 6, in which Bedini states that God created two worlds. This imperfect land beneath the moon's plane is subject to cycles of creation and destruction as well as disorderly movement. Yet the heavens above the moon's plane are eternal, with no beginning or end. They should move forever in a perfect circle. What is being described here is the Aristotelian model of the cosmos, which held that matter was largely composed of 4 elements: earth, water, air, and fire. All matter found on the Earth contained varying amounts of these, which determine the properties of that object. But these elements were mutable, meaning that the composition of objects could change and were subject to degradation. In his model, the Earth was at the foundation, with water floating over parts of it, surrounded by air, above which was a sphere of fire. But beyond the sphere of fire, we're suddenly in a different realm entirely, a celestial one, where the objects are not made of these mutable elements, but are, instead, composed of a 5th element, known as the aether or quintessence. This material was eternal and unchanging, and had different fundamental properties that required these objects to move with a perfect, uniform, and eternal motion. That motion, he held, had to be in perfect circles at constant speeds. Yet this contrasts starkly with observation. While the motion of the stars is extremely constant, the motion of the sun, moon, and planets with respect to these background stars is irregular. They speed up and slow down. For some planets, it can even reverse entirely, a phenomenon known as retrograde motion. We are introduced to this concept in episode 4, in which Graz is observing the motion of the planet Mars through the constellations, marveling at how it appears to follow the Aristotelian precepts, moving in a perfect circle with a uniform speed. He's warned in a pub that it's unfortunate that he started his observations when he did, or he would have noticed sooner. We very quickly find out what was meant when Graz discovers that Mars's apparent motion in the sky has slowed down and is now standing still on the verge of reversing. This is impossible to explain with the bare Aristotelian assumptions. In response, the Greek astronomers tried to come up with a model that could explain these motions while still holding true to these philosophical presuppositions. Another of the presuppositions is that the Earth did not rotate on an axis. Rather, the daily motion of the cosmos was caused by the rotation of the entire heavens about the Earth every 24 hours. Ptolemy refers to this as the first primary motion of the heavens. To support this, Ptolemy argues that if the Earth rotated, the clouds, which are not affixed to the Earth, should be left behind, thus forcing the movement of the clouds to always be in one direction, contrary to observation. However, not all astronomers made this assumption. Specifically, Heraclides of Pontus, from the 4th century BCE and mentioned in episode 8, proposed that the Earth did rotate. Lastly, the Greek astronomers held that the Earth was at the center of all of this, hence geocentrism. And the reason they placed the Earth at the center is fairly well explained in the first episode. Heavy things have a direction they seem to want to fall. There was no notion that the mass of objects itself creates this attraction, so the natural assumption was that there was simply a point in the cosmos to which all things were attracted, with heavier things being more strongly attracted and more diffuse things less so. Thus, since the element of Earth was the heaviest, it should naturally fall to this position, whereas the other elements, being lighter, were stacked as described previously. The heavenly aether, again, was given its own realm. These presumed facts made up the core of astronomical thinking for nearly 2,000 years and were the foundations for the models that various astronomers attempted to create to explain the motions during the Greek era. The most important of these, which is repeatedly mentioned throughout the series, is that of Claudius Ptolemy from the 2nd century CE, who wrote the most influential text on astronomy for the next 1,500 years, the Almagest. To explain this non-uniform motion, Ptolemy used several tricks, two of which get mentioned in the series. The first is known as an eccentric. This simply means moving the center of the sphere that carries the object away from the Earth. It still moves in a perfect circle at a uniform speed, but by being slightly displaced, it will appear to move faster on the part of its orbit nearer the Earth and more slowly when further away. While this works well enough for the Sun, which only slows down and speeds up, it can't explain retrograde motion. Thus, Ptolemy's second trick is to add another, smaller sphere to the larger primary sphere. This is known as an epicycle. When the object is on the portion of the epicycle's circle that carries it in the same direction as the primary sphere, known as the deferent, the motions will add together and it moves faster. When on the opposite side, it appears to move more slowly, and if the rotational speed of the epicycle is fast enough, it can make it briefly appear to move backwards. By combining these concepts with another, known as an equant, Ptolemy was largely able to reproduce the motions of the planets, creating a model that could be used to calculate the position of these objects in the past or future. Pop history tends to leave off the next part of the story, leaving people to assume that Ptolemy's model was accepted uncritically for over 1,000 years, a trap which Orb very nearly falls into. But this wasn't the case at all. Within a century or two after Ptolemy, astronomers were already finding that the predictions were off. But why? Astronomers examined the various components of the model and assumed that the weakest points were almost certain to be the various parameters, the key values, that were derived through observation and therefore subject to error. The Aristotelian foundations built on pure logic continued to appear far more solid. Thus, we find several centuries of astronomers, particularly in Islamic countries in the Middle East, trying to revise these key figures of the model, things like the length of the year and the size and speed of the various spheres. But when that failed, they began trying to rearrange the spheres. They even introduced some slight variations, such as an idea from Al-Tusi, in which he considered spheres rolling within spheres instead of on them. Victory always seemed near, especially given that the models would work relatively well for the lifetime of a single human, and it was only as the errors accumulated that the problems really stood out. Thus, the scientific process was slow to play out and saw little success, which is why this era tends to get left out. Orb does address this period somewhat. First is a brief mention in episode 7 that Arabian heretics have revised ancient Greek astronomy. The second is from the character of Count Piast in episodes 8 and 9, in which he learns that Piast is attempting to revise the geocentric model and perfect it. However, these very generic statements are the entirety of the recognition that there were attempts at reform. But they are interesting in that, taken together, they actually reference a specific attempt at the reformation of the geocentric model. Specifically, it is shown that Piast's mentor introduced a second epicycle. The diagram presented is virtually identical to one from Ibn al-Shatir's lunar model. This model attempted to address a problem that was created when Ptolemy tried to solve another problem that he found with Hipparchus's lunar model. Specifically, Hipparchus's lunar model was simply a moon on an epicycle. This made reasonably accurate predictions when the moon was in the new or full phase, but had considerable problems when at first and third quarter. Ptolemy's solution was to move the center of the moon's large circle, the deferent, off of the Earth onto another small sphere, which would pull the deferent closer to the Earth during these two phases. This would amplify the effect of the epicycle and allow the model to make accurate predictions on the position of the moon in the sky. However, the amount by which it would have pulled the moon closer implied that the moon's apparent size in the sky would change notably to the visible eye. Al-Shatir's double epicycle achieves the same result without the change in apparent size. Ibn al-Shatir is given a brief shout-out in episode 25. Returning to the larger story of astronomy, some fail to recognize the progress that was made with attempts to revise the geocentric model. Instead, they suggest that astronomy failed to progress at all, and claim that it was actively suppressed by the Christian Church. Throughout the entire series, we find the Inquisition hot on the heels of heretics who would dare challenge the geocentric model. But was the Church opposed to astronomy? The answer is complicated, and I have an entire video exploring this in much more detail. The short version is that we need to recognize that astronomy in this time period was far more diverse than we tend to think of it today. It was more than just mathematical models. It also included using the heavens for practical purposes, timekeeping, and navigation. It included the philosophical arguments about the nature of the cosmos and our position in it, such as the Aristotelian assumptions we've just discussed. It also includes attempting to draw meaning from the heavens through astrology. The degree to which the Church opposed astronomy is strongly dependent on exactly what form of astronomy we're talking about, and when. Broadly speaking, the Church was always in favor of using astronomy for practical purposes. It developed methods for telling time at night using the stars and a complicated set of mathematics to determine the correct date for Easter, based on knowing the precise dates of the spring equinox. The Church was somewhat less permissive when it came to the philosophical arguments. This was most aptly demonstrated in the 13th century, when new works from Aristotle and Plato were first translated into Latin, and were excitedly discussed by the students at the University of Paris. The Church issued a series of condemnations, initially banning some of the texts entirely. But very quickly, we find that this was relaxed, and the Church instead issued more specific condemnations regarding particular answers to the philosophical questions these texts contained, some of which were astronomical in nature. For example, one of the questions that Aristotle grapples with is whether or not the cosmos is eternal. Since his model posited a cosmos composed of the aether, which is not subject to corruption, Aristotle assumed that it was. This obviously conflicted with the Christian account in which God created the universe at a specific point in the past. Thus, when a potential answer to a question directly contradicted Scripture, it was banned. The view on astrology from the Church was even more complicated. Genesis clearly states that the stars can be looked to for signs, and even Jesus' birth was supposedly heralded with a celestial omen in the form of the Star of Bethlehem. Thus, Christianity was forced to be permissive of some forms of astrology, but continually wrestled with exactly what that limit was. By and large, the line tended to be drawn at having to do with the fates of humans, as this would contradict the doctrine of free will. Yet we still find various church members arguing that the stars didn't control human destiny, but merely communicated God's will, and that it was up to humans whether or not to accept these instructions. Thus, astrology did not inherently undermine free will, but enhanced it by allowing us to go along with God's plan. When various church figures do target astronomy, there are a few specific reasons they tend to do so. One of them is expressed in the series in episode 6, in which an abbot states, "Curiosity is a sin." Indeed, curiosity was considered a sin in the medieval church. The reasoning is akin to the sin of gluttony. Eating is necessary, but too much is ruinous. Similarly, a little knowledge is good, but too much can lead to one of the deadly sins, pride. Returning to the mathematical models, the church was largely silent on the position of the Earth. Only once the Protestant Reformation began, in the early 1500s, do we find the church beginning to take any position. Yet even then, it was hesitant to do so. Copernicus published his major work on the heliocentric model in 1543, and it initially saw no pushback from the church. This may have been due to the fact that Andreas Osiander, who was called in to oversee the printing when Copernicus' student George Joachim Rheticus was called away. Osiander inserted an unauthorized preface stating that the model was not intended to be taken as a literal description of the arrangement of the cosmos, but a convenient mathematical model. Regardless, the church still made use of Copernicus' work to help them reform the calendar to the Gregorian calendar that we still use today. Even Kepler's heliocentric model, published in 1609, was not immediately met with condemnation, even though Kepler was a devout Lutheran. Indeed, the Catholic Church repeatedly attempted to convert Kepler, and Kepler even agreed to call himself Catholic, but would not agree to espouse views which he held to be false. Thus, the Catholic Church rejected his conditional Catholicism, but took no direct action against him, likely in part because if he was not Catholic, he did not fall under their religious jurisdiction. It was only as Galileo began using the telescope and publishing his works supporting heliocentrism that the Church finally placed the various heliocentric texts on the index of banned books. But even then, the Church would still allow many of the works to be published if they made it clear, as Osiander had, that they were not attempting to assert the true order of the cosmos. Thus, their resistance to heliocentrism was weak at best, at least up until this point. This, of course, brings us to the Galileo affair. And again, this story is far more complicated than pop history lets on. Certainly, heliocentrism was at the very core of Galileo's trial. But through a careful dissection of how the affair played out, we can see that the church was largely making things up as they went along. As Galileo continued to expound on heliocentrism, the church realized that it needed to establish an official position, and in 1615, we find that the Inquisition discussed the matter with the Gionazi Attavanti. In this, they affirmed that Galileo had advocated the heliocentric model, but that the church needed to determine the theological status of Scripture either for or against heliocentrism before proceeding against him. It took until the 24th of February, 1616, for the Inquisition to conclude that the heliocentric model was foolish and absurd in philosophy, and formally heretical since it explicitly contradicts in many places the sense of Holy Scripture according to the literal meaning of the words, and according to the common interpretations and understanding of the Holy Fathers and the doctors of theology. Only once this conclusion was reached did the Church order Galileo to abstain completely from teaching or defending this doctrine and opinion, or from discussing it. Yet in 1632, Galileo published his dialogue concerning the two chief world systems. To be fair, Galileo had sought explicit permission from Pope Urban VIII to write such a work, and was granted it, so long as he made it clear that the work was entirely hypothetical, and that Galileo included some of the arguments from Urban himself regarding the omnipotence of God. As the name suggests, this was not a scientific treatise as we would understand them today. Rather, it was a dialogue between various characters who would debate various ideas. However, the author of the dialogues can easily have one of the speakers ineffectively or simply fail to make an argument that the author wants the reader to find disfavorable, neutering the argument instead of addressing it. And this is largely what Galileo did. In this dialogue, he creates a character named Simplico to defend the geocentric position. Although Galileo claims that this was based on the Aristotelian philosopher Simplicus, it was also clearly a play on words to indicate that the speaker was a simpleton, and many believe that it was based on a certain contemporary philosopher to Galileo, thereby offering a thinly veiled insult. Worse yet, the arguments that Urban had required be included also came from the mouth of this character. This caused Galileo to lose what little favor he had and brought him into direct conflict with the Inquisition. Galileo faced trial in 1633 and was threatened with torture, but none was actually ever employed as Galileo recanted. But having already been warned once, he was placed under house arrest for the rest of his life. What we can see through this entire timeline is that the admonition from the Church against heliocentrism came only very late in its discussion, some 80 years after Copernicus had written De Revolutionibus, which wasn't even his first proposal of heliocentrism. That came in 1514 in a work known as the Commentariolus, the Little Commentary. The Church's response was extremely delayed, as it first censored the books, insisting that they present heliocentrism as a hypothetical, and only took direct action against Galileo when he defied this order. And even then, Galileo was never tortured or executed. Some of you may be wondering about the case of Giordano Bruno, who was burned at the stake in 1600. While Bruno certainly argued in favor of a non-orthodox cosmology, this was nowhere near the core of the charges against him. As we just saw, the Church did not have any position on the arrangement of the cosmos at that point. Unfortunately, the records of Bruno's trials have been lost to time. What little we do have only tells us that Bruno viewed the cosmos as infinite. However, Bruno was known to have committed numerous other heresies, which were likely contributing, if not more significant factors, and included denying several core Catholic doctrines, including eternal damnations, the Trinity, the divinity of Christ, the virginity of Mary, and even transubstantiation. So, having debunked the notion that the Church was staunchly against heliocentrism, let's begin to examine heliocentrism itself. Heliocentrism is, at its core, just the argument that the Sun is the center of the solar system. As alluded to in Episode 8, the earliest proposal of such a model is attributed to Aristarchus of Samos from the 3rd century BCE. Unfortunately, as with most of the Greek astronomers, Aristarchus's original work on this subject is lost. What little we do know of it comes from a book entitled The Sand Reckoner by Archimedes, in which he tells us that Aristarchus proposed that the fixed stars and the sun remain unmoved, that the Earth revolves about the sun on the circumference of a circle, the sun lying in the middle of the orbit. It is unclear whether this was simply a qualitative model, or if Aristarchus was able to derive and calibrate a fully mathematical one capable of making predictions. Regardless, Ptolemy's model was the one that survived, and heliocentrism largely faded from the astronomical imagination. It was first revived by Copernicus in 1514 in his Commentariolus, but this text was not widely distributed. It wasn't until 1543, when Copernicus published his De Revolutionibus, that heliocentrism truly got public attention. There's a bit of a myth regarding this text, that it was largely ignored. This is because we don't find other astronomers publishing discussions, commentaries, or refutations of it. However, examination of the extant copies of the text frequently demonstrate that they often have extensive notes taken by their owners in the margins, indicating that the books were being read and given due consideration, so it's not clear why it didn't receive wider commentary. But while Copernicus was able to derive a mathematical model, he was unable to shake himself of the Aristotelian philosophy. He continued to assume perfect circles with uniform motion and was fully aware that simply placing the planets on these would not make accurate predictions. As such, he was forced to resort to eccentric circles, epicycles, and equants. He adopted some of the Islamic innovations, such as Al-Tusi's spheres rolling within spheres. But ultimately, Copernicus's model did not offer significant simplifications compared to Ptolemy's, nor did it offer particularly improved predictions. Thus, heliocentrism itself needed immediate refinement, which came relatively swiftly from the astronomer Johannes Kepler. Kepler had been taught geocentrism as it was still the default assumption for the time. But his teacher, Michael Meslin, also introduced him to Copernicus's work. While Kepler favored Copernicus's heliocentric model, he was well aware of its issues. In the introduction to his 1609 work, Astronomy Nova, Kepler points out that in August and September of 1593, the observed position of Mars in the sky was nearly 5 degrees off from the position predicted by any of the models. Kepler ultimately broke free of the Aristotelian assumptions. He replaced the perfect circles with ellipses and allowed the speed to vary such that the objects move faster when closer to the Sun and more slowly when further away. Kepler states that this new model fit the data perfectly and made the 5-degree error of Mars disappear entirely. As a brief aside, Kepler was not actually the first to propose using ellipses for astronomical orbits. That recognition actually goes to the first character directly depicted in orb that is a true historical character, Albert Brzezowski. However, Brzezowski only applied an ellipse to the orbit of the Moon. Brzezowski was a lecturer on Aristotelian philosophy at Krakow Academy, where he taught a young Copernicus. In theory, this would give a through line from the original characters in this series to Kepler. But there is no evidence that Kepler was inspired by or even aware of Brzezowski's hypothesis. It should be noted that the events depicted from Brzezowski's childhood are entirely speculative, and little is known about his life prior to his graduation at the age of 23. In episode 10, we get a brief retcon of the history of Tycho Brahe and Kepler in Bedini's character. As he works on his version of the heliocentric model, he's frustrated that his essentially Copernican model isn't matching the records. He questions whether it's the model that's wrong or the observations. This is essentially the question that Tycho Brahe had asked himself. As a child, he was frustrated to find an eclipse occurred a day later than astronomical models had predicted. He realized that the models were built on observations and thus made it his life's goal to produce the most precise observations ever recorded. Bedini then stumbles on the notion of elliptical orbits, and we see a tiny glimpse into Kepler's methods for calibrating his model, which requires observing Mars at the same position in its orbit, which occurs every 687 days or 1.88 years. Of course, the Earth will be in 2 different positions in its orbit, so trigonometry can be used to determine the true position of Mars about its orbit at those times. From Brahe's records, Kepler had 5 such pairs of observations of Mars, allowing him to determine Mars's position at 5 different points along its orbit. He could then fit an ellipse to these points. Of course, while Kepler's model offered significant improvements in the predictions it offered, it still suffered from not having a firm theoretical basis. In episode 11, Bedini says something similar, noting that there is much left to explain in terms of natural philosophy. While Copernicus and Kepler had made leaps forward in astronomy, physics still needed to catch up. We see one of the objections stemming from this in episode 2. There, Rafal objects to a moving Earth, noting that if he jumps, he lands precisely where he jumped from. This seemingly disproves the Earth moving in the Aristotelian worldview because Aristotle assumes that bodies naturally want to be at rest. Unless actively being pushed by a force, they would slow down until they were no longer moving. This is essentially the same argument that Ptolemy is using against a moving Earth, which we described previously with respect to clouds. Physics had not yet developed the notions of friction or inertia, which could explain this. Meanwhile, many of the initial arguments presented for heliocentrism were more so attacks on geocentrism. One argument we often hear in favor of heliocentrism is its elegant simplicity in comparison to the complicated arrangement of epicycles, eccentrics, and equants from Ptolemy. An argument from simplicity even pops up in episode 6, in which Bedini asks Oxy, "You can tell which is simpler, right?" This argument is essentially invoking Occam's razor, which is a principle that is popularly paraphrased as, "Of 2 competing theories, the simpler explanation is to be preferred." The name refers to the 13th century theologian William of Occam, although Occam is not actually known to have made this argument. Other philosophers, both contemporary to Occam as well as earlier, did make similar arguments. So such an argument is not out of place. However, this is not one of the arguments Copernicus actually made in favor of his own model. Instead, Copernicus notes the rather capricious arrangement of the planets in the geocentric model. Specifically, the geocentric model placed Mercury and Venus closer to the Earth than the Sun, but Mars, Jupiter, and Saturn more distant. Furthermore, Mercury and Venus are never observed too far away from the Sun in the sky. To account for this, Ptolemy made the speed of their deferent circles equal to that of the Sun, and accounted for their distance from it almost exclusively through their epicycles. However, Mars, Jupiter, and Saturn are free to be any distance in the sky from the Sun. Essentially, Copernicus asks what principle should tie Mercury and Venus to the Sun, but not the other planets. Lastly, to account for the angular distance that Venus could obtain from the Sun, as much as 45 degrees, its epicycle would need to be massive, so much so that it would crash through the spheres of the other planets. This was illustrated in this figure, which shows the geocentric paths of the Sun, Mercury, and Venus all intersecting. A simplified version of this diagram is shown in episode 2. In this, Kepler describes this geocentric pattern as unintelligibly intricate, for the continuation is boundless, never returning to its previous path. Kepler is effectively saying that this pattern is utter chaos, which did not fit with the perfect and divine conception of the cosmos Aristotle laid out. While the first support for Kepler's heliocentric model was that it produced better predictions, this alone was not going to do away with centuries of natural philosophy. What would be needed would be observational evidence. We're given a rather distorted example of this in episode 9. There, Count Piast has Oxy reproduce an observation that Piast made in his youth, in which he claims to have seen Venus in its final phase. This is a very awkward phrasing, but it's quickly revealed that this is meant to signify that Venus was observed to be illuminated more than half. However, this is impossible in the geocentric model since, in it, Venus is closer to the Earth than the Sun, with the motion of its deferent linked to the Sun's. This meant that no matter where you place Venus in its geocentric orbit, most of the lit side would be facing away from the Earth as illustrated here. However, this is a very anachronistic argument. In reality, even at its closest approach to us, Venus's angular size is only just over 1 minute of arc. But at this position, its lit side would be entirely facing the Sun, and we wouldn't be able to see the planet at all since none of it is lit from our point of view. And it would be up during the day. For Venus to be viewed more than half lit from our point of view, it would have to be further from us than the Sun. While this is allowable in the heliocentric model, at that greater distance, its angular size is smaller than can be seen with the human eye. As such, the phases of Venus wasn't discovered until 1610, thanks to Galileo's use of the telescope. So, while the nature of the observation depicted is sound, the circumstances are fictional. Meanwhile, the criticisms of heliocentrism on the grounds of natural philosophy were also being addressed. Copernicus argued against the notion that the Earth must occupy the central position because there is a universal down to which it would fall. Rather, he states, "I myself think that gravity or heaviness is nothing except a certain natural appetency implanted in the parts by the divine providence of the universal artisan, in order that they should unite with one another in their oneness and wholeness, and come together in the form of a globe. It is believable that this effect is present in the Sun, Moon, and other bright planets, and that through its efficacy they remain in the spherical figure in which they are visible, though they nevertheless accomplish their circular movements in many different ways." In other words, he says that God can make gravity attract objects towards anything he likes, not just a single center, and that one of the consequences of this is that they would become round. Since we observe the Sun and Moon as round, they too may have gravity. But this does not address the belief that objects should naturally slow down. Kepler attempted to address this. By observing sunspots, which can be visible to the naked eye when viewed through a proper filter, Kepler was aware that the Sun rotated. He proposed that the gravitational attraction of the Sun was similar to a magnetic force, and perhaps the solar rotation drew the planets along with it, with the ones closer to the Sun being pulled more quickly and those further out less so. It wasn't until 1687, when Isaac Newton published his Principia, that this problem was fully solved. Further observations continued to put nails in the geocentric coffin. In 1727, James Bradley noticed that the position of stars seemed to change by a minute amount in a cyclical pattern throughout the year. Exactly when and how much varied for each star, but this phenomenon became known as the aberration of starlight, and is neatly explained by a moving Earth and a fixed speed of light. But the most definitive proof came when the accuracy of telescopes increased enough to allow astronomers to measure parallax. This is a shift in the apparent position of a nearby object in relation to more distant ones, caused by observing the nearer object from different positions. It's easy to see this by holding out a finger and viewing it with each of your eyes independently. In 1838, the astronomer Friedrich Bessel was the first to demonstrate this for the star 61 Cygni, thereby proving that the Earth had moved between the observations. By that time, most astronomers already accepted heliocentrism, but with these discoveries, there could no longer be any serious doubt. At this point, we've covered a pretty comprehensive history of the debate between geocentrism and heliocentrism, but there are still several other miscellaneous references to point out. In particular, I found Count Piast to be an interesting character, as there are some elements of the 16th century Danish astronomer Tycho Brahe in his character. However, Brahe had given up on the geocentric model. Rather, he proposed a model in which the Earth was at the center, the Sun and Moon orbited the Earth, but all the other planets orbited the Sun. But like Piast, he made it his life's work to amass countless observations that might be used to calibrate his model. Additionally, we learned that Piast inherited a gold astrolabe. This almost certainly would not have been pure gold, as gold is very soft, and would therefore not be suitable for precision instrumentation. Rather, this reminds me of some of Brahe's instruments, which were gilded, essentially gold-plated, as this would enhance both the appearance of the instrument and make it more resistant to tarnish. Lastly, Piast throws off some serious Brahe vibes in episode 9, in which he hands over the key to his records, wondering at the meaning of his life if he had not achieved the purpose with which he had set out. Brahe expressed similar sentiments on his deathbed, saying, "Let me not seem to have lived in vain." In episode 8, there are several names mentioned without much context. The first is Peter Abelard. This name is brought up in the context of universals. In short, universals are properties of objects that appear in two or more of them. For example, if crows are black, then black can be considered a universal property of a crow. From there, philosophers discussed whether or not the property could exist outside of the objects. In short, was there an extrinsic blackness that existed independently of the object? Peter Abelard took the position that such properties are simply labels that humans attach to things and are not extrinsic. This is called the nominalist position, which Bedini tells us he supports. Jolenta responds that she does as well, and is in agreement with the aforementioned William of Ockham. Another is Philolaus, who was a follower of the Pythagorean school. As with so many Greek writers, none of Pythagoras' writings on astronomy have survived, and what we do know of them comes from Philolaus. This model is interesting in that it suggests that the Earth orbits a central fire, which is invisible, and the model also contains an anti-Earth called Antikython, which is not well understood as the surviving texts are not clear on its nature. Another historic figure we get a reference to is Lucretius. This 1st century BCE philosopher is famous for his poem De Natura Rerum, on the nature of things. In it, he essentially proposes evolution nearly 1900 years before Darwin. In episode 12, we learned that a cryptographic message was decoded using frequency analysis. As the name suggests, a frequency analysis is simply examining how frequently something occurs. Using this, it becomes fairly straightforward to break a simple letter substitution cipher by determining which letters occur the most frequently and knowing which letters are the most common in the language in question. This method is entirely appropriate, as the technique was developed in the 9th century by the Arab mathematician Al-Kindi. However, a piece of information that is utterly out of place historically comes from episode 6, in which Bedini reads that the Sun is 109 times the size of the Earth. This is the correct value, but the size of the Sun would be determined geometrically using its angular size and distance. Thus, the determination of the size of the Sun depends on a correct determination of its distance, which was not available in the 15th century. Rather, the error in the distance of the Sun didn't fall under 10% until 1672. Thus, this statement is horribly ahistorical. There's another error in episode 24. In this, a young Radzewski excitedly tells his father that he discovered that there's a star in the north that doesn't appear to move, as it lies at the point about which all stars seem to rotate. His father tells him that this star is the star Polaris. However, the rotational axis of the Earth wobbles in a 26,000-year cycle. This is known as axial precession, and it means that the position of the north celestial pole, the point about which the stars seem to rotate, drifts in a large circle over that period. The result is that, in the mid-15th century, Polaris was 3 3/4 degrees away from the celestial pole and would thus make a circle of a notable size around it. It was significant enough that, in the 16th century, sailing manuals that used the star for navigation needed to explain how to account for this motion, lest navigators not correctly determine their headings. Today, Polaris is only 2/3 of a degree away from the pole, making the circle it makes about the pole significantly smaller. Overall, Orb is an interesting bit of historical fanfiction. Much of it is clearly inspired by actual historical events, although large liberties are taken with the timing of knowledge and the suppression thereof. That being said, I appreciate this anime because it begins to dispel one of the long-standing myths in the history of astronomy, that nothing happened in astronomy between the time of Ptolemy and Copernicus. The reality is that humans have always gazed upon the stars in wonder and attempted to understand the secrets of the heavens. I hope that this exploration has inspired you to look at Orb with new eyes, understanding not just its story, but the history of astronomy before the telescope.